Good evening, ladies and gentlemen. Can everybody see me and everybody hear me? Okay, awesome. That is good. So, how was your first day of official classes at UP? I can imagine it's very long. Are most of your classes online or in person? So, hopefully, in about a month or two, you guys will be able to sit in classes on campus. University is currently phasing in everybody back. So currently postgrads on campus, honor students on campus, third years on campus. So next step will be to get the second years back on campus and then the first years. So I am Mr. Heistek Grobler and I will be teaching you this semester. So let's wait another minute or so for more of our class friends to join. So if you have any questions during my lectures, you are more than welcome to interrupt me anytime. You can use the chat function on Blackboard Collaborate, or you can unmute your mic and speak to me directly. Okay, so I think we can start with tonight's lecture. So this is just going to be a introduction lecture of what this course is going to be about, and also what we're going to do, and just a few cool astronomy things that me and people around me have been up to. So I'm just going to turn off my camera to save bandwidth. So in tonight's lecture, we're going to go, like I say, go for the course information, what I'm going to do in the course, who am I, and then we're going to start a bit with introductory on astronomy. So I just want to make sure that we take SCI 154 along with Physics 134 because I see both are the first semester. I assume so. So, like I said, I am Mr. Heistek Grobler. I'm a lecturer, researcher at the Department of Physics here at the University of Pretoria. My office is room 568. So I will have consultation times Mondays and Tuesdays on campus. So I have an open door policy where you just can pop in anytime if you have any questions on Mondays and Tuesdays. Besides Mondays and Tuesdays, we can set up a consultation any other time during the week, and we can set up consultation times via Google Meets, Zoom, Skype, and any other videoing platform that you guys prefer. So all our formal communication for the course will happen through Blackboard Collaborate. Uh, every notification on Blackboard Collaborate will have an automated email as well. All our material, your study guide, lecture notes will also be available on ClickUp. And then I will also create a WhatsApp group and a Discord channel that will also serve as communication mediums. So everything pasted and posted on Blackboards will or ClickUp will also be available on the other channels as well. So what if only one takes SCI 154? Yeah, you can only take one of them. I'm not sure what courses or what degree you are enrolled in. The subject is open to all faculties. So it all depends on what you're studying. So in this class, we're going to have physicists, computer scientists, engineers, some people from accounting, some people from education. So this module is open for everyone. So yes, so for now, this will be an online module unless universities' COVID regulations change, and then perhaps in 2 or 3 months, we will have this lecture in person on campus. Yes, that is where I'm going now. So our prescribed textbook for this module is Horizons, Exploring the Universe, the 14th edition. The bookstore on campus has copies of this book. And I know if you know where to search on the internet, you'll probably find a PDF version of this book somewhere. This is how the textbook looks like. It is a really good textbook. An additional textbook this is not a prescribed textbook, but just an additional textbook is astronomy, and it's a open source textbook that you can just download from this site. I've posted links of OpenStax, and you're more than welcome to use this textbook as well. But our primary textbook and the prescribed textbook is the Horizons textbook. And this is how the additional textbook looks like. So evaluation for this course will consist out of a semester test, one big assignment, a few pop-up quizzes, and a written exam. So before the end of the week, I will upload the study guide, and in the study guide will be the date for the semester test, the assignments, and the exam. So the weighting for your semester mark and final mark will be the semester test will count 50% of your semester mark. The assignment will count 40% of your semester mark, and quizzes 10% of your semester mark. So the quizzes will be one every week, perhaps one every second week, perhaps. I will also use the quizzes to get a feel on the class of how you are understanding the work that we are covering as well. And I will also use the quizzes as attendance register. So your final mark will be 50% for the semester mark, 50% for your exam mark, and the final mark will be 100%. So keep in mind, this class is a democracy. So the semester test and the assignment can be changed, well, the date of it can be changed if the majority of the class votes on a new date or a better date, then I am willing to change it. The exam date, unfortunately, I cannot change. The university has a committee that schedules the exam timetable, so unfortunately that cannot be changed, but a semester test and the assignment I can change. And there will be no sick tests. So if you have a illness or something happened, I need a medical certificate within 3 days of the test, and from there on, we will take it from there. And then no assignments will be accepted after the stipulated submission date and time. And then very, very, very important, to get entrance into the exam, you need a minimum mark of 50% for your semester mark. So the aim of this course is to give you guys a non-technical introduction and overview of astronomy, and to familiarize yourself with some of the methods, techniques that we use in astronomy, and also to get the knowledge base to explore our universe and the wonderful different phenomena in our universe. So we will discuss basic scientific principles and concept, but all of you will understand it. You don't need a pre-science education for this. And we will only be doing basic math in this course. And most of the course will take a practical nature, and hopefully this will prickle your interests in astronomy. So, about myself, I'm Mr. Heistek Grobler. I was previously at the University of Johannesburg. I moved over to UP about 3 years ago, where I am a lecturer and researcher. I'm also a researcher at the South African Radio Astronomy Observatory. That is a part of that falls under NRF, and the site I am as the Hartbeespoort Radio Astronomy Observatory formerly known as HART-RAL. So a few cool astronomy stuff I've been involved with, and a few of my other colleagues has been involved with, is going to show you now. Yes, you can go ahead. Miss McKenna, I see you have raised your hand. You can't see the slides. Does anybody else have a problem seeing the slides, or can everyone see the slides? So probably, Ms. McKenna, just refresh your page and hopefully that will solve your problem. So all of our lectures will be recorded. You'll be able to download them from Blackboard Collaborate. I will also upload them to YouTube and also to Google Drive. So after the lectures, I will give you links to Google Drive where you can download it, and a link to YouTube where you can watch it. I will also give you the links for the previous year's lectures as well. So I've taught this course in 2020 and 2021, so this is my third year teaching this course, so you'll be able to have the previous lectures available as well. So in my undergrad, this is one of my science projects that I've done, is to build a concrete canoe that different universities actually raced against one another. So this was one of my projects that kept me busy for about a year. I have also built a rocket and satellite that we launched. Yes, Ms. McKenna, I see you raised your hand again. So unfortunately, we are not going to build a rocket for this course, but this is the image we captured from first stage separation. And we launched a satellite into the atmosphere where we collected atmospheric data. And then we landed, or retrieved the rocket and satellite again. So this was part of the CanSat challenge. So the challenge was to build a satellite that's the size of a Cocan, see how high you can launch it into the air, get data, and land, bring it back safely to the ground again. I've also spent some time at the South African Large Telescope, or better known as SALT, down in Sutherland. Are you guys all familiar with SALT? Okay, so I see a lot of yeses and a few no's in between. So we're going to discuss SALT. So SALT is the largest optical telescope in the Southern Hemisphere, and it sits in the Northern Cape in Sutherland. So this is the observatory where I am based most of the time. It's the Hartebeespoort Radio Astronomy Observatory. It forms part of the South African Radio Astronomy Observatory. So this observatory is halfway between Krugersdorp and Hartebeespoort Dam. It's a radio telescope. So we will cover the difference between a normal optical telescope and radio telescope in this module. But this site was originally built in the 1960s to do tracking and telemetry on the Apollo spacecraft. So 3 of these antennas was built 120 degrees from each other. So when the Earth turns and the moon is out of view of the Apollo spacecraft, then tracking, telemetry, and communications can be done through the next antenna. And all this information was passed to Mission Control in Houston, Texas. So after the Apollo missions was finished, South Africa took control over the antenna and transformed it into a radio telescope. So it was first controlled by the CSIR from the 1970s until the 1990s, and then the NRF took control over the telescope, and it's still being used ever since. So this telescope is 10 stories high and 26 meters in diameter. And this is the first radio telescope in South Africa. The other radio telescope in South Africa is the Meerkat telescope that you've all heard of. So Meerkat also falls under the control of the South African Radio Astronomy Observatory, or SARAO in short. And the Meerkat telescope will become the SKA. So at the Hartebeespoort Observatory, we also have 3 giant lasers. You can see one of them in this image. So we call this laser a Satellite Laser Ranger, or SLR in short. So we use these lasers to determine the distance of satellites and where the satellites are in their orbit. So we literally shoot a satellite with this laser. The laser reflects back from the satellite. We record how long the laser takes to return back to the observatory. And then from there on, we can calculate to an accuracy of 3 millimeters where a satellite is in its orbit. So this means when a new satellite gets launched, we do priority tracking missions to make sure the satellite is in its correct position in orbit. And we also make use of this laser to double check that all the satellites are where they're supposed to. So if a satellite has drifted out of orbit, then we let a company owner or organization know your satellite has drifted, and they need to fire up their retro rockets to push the satellite back in orbit. So this is not exactly the Doppler effect. So you know what the speed of the laser is. So we record for what is the time for the laser to come back to the origin from where they shoot it. And from there on, we can calculate the orbit of the satellite. So yes, we will learn a bit about of redshifts and blue shifts as well. So there's not exactly LiDAR. So there's not a form of radar or sonar or LiDAR. It is literally just PMF. So if you know the speed of something and the time of something, then you can calculate exactly where it is. And then we also have another laser called the Lunar Laser Ranger. The Apollo missions left behind giant reflector plates on the surface of the moon. We know the distance of the moon, we know the coordinates of those reflector plates, and on the same principle, we can calculate the orbit of the moon, how it differs day by day, month by month, year by year, and we can see how the moon is oscillating a bit closer to Earth, a bit further away from Earth, and how the orbit of the moon is increasing each year. And this is one of my other favorite observatories around the world. This is the Green Bank Observatory in the United States. It's situated in West Virginia. So this is the world's largest single antenna radio telescope that is also movable. So it can move up, down, left, right, turn 360 degrees, tilt 90 degrees downwards. It's higher than the Eiffel Tower, and it is 110 meters in diameter. So it is, if you do the conversions, give perspective, it's about 50 stories high. And the area of the dish is bigger than a rugby field. So here you can see me in the center in front of the telescope. So I have spent a lot of time at this observatory. This is probably one of the coldest days I've ever experienced. So this was minus 27 degrees Celsius outside. So one thing to remember about telescopes, if we have an optical telescope, then we cannot have any light pollution near the telescope. So for example, the way optical telescopes are in Sutherland, there is literally no light sources near the telescope. So it's a light pollution exclusion zone. So the little town of Sutherland, when it is sundown, they have to close shutters before in front of their windows so you don't have light interference on the telescopes. So for radio telescopes, we have a radio exclusion zone. So in a certain radius around the telescope, you are not allowed to have anything that can cause RFI, radio frequency interference, and EMI, electromagnetic interference, because that will cause interference on the telescope. So that brings me to this. So how do radio telescopes work? So that is something I will discuss in a moment. So in this image, what do you guess this is? Yes, it's a microwave, but why is the microwave in a steel box? Yes, to stop the EMI from the telescope. So that's a 3 centimeter thick steel box. And the radio telescope will detect the microwaves from the oven. So at most radio astronomy observatories, you're not allowed to have a microwave oven unless you can put it in some sort of a Faraday cage, like in this example right here. So this is at the Green Bank telescope. So what do you pick up interesting from this sign? Yes, you're only allowed to drive with diesel vehicles on the site. You guys have any idea why? Because the telescope is so sensitive, it picks up the spark plug in a petrol engine, and the spark plug causes interference on the telescope. So just to give you an idea, let me go back to the slide of the Green Bank telescope. This telescope has the ability to pick up the energy of a snowflake hitting the ground. So theoretically, if you would put a cell phone on Mars, you would completely blind this telescope. So therefore, you can only drive with diesel vehicles on the site. You also cannot use a digital camera too close to the telescope because the telescope will pick up the shutter from the camera. So how does it operate at all on Earth? So around this telescope, we have radio exclusion zones where the area is designed that you have no interference on the telescope. And if there's interference and you are caught, then you get fined or even jailed. In the US, if you cause interference on for example, the Green Bank telescope, you are fined a $2,000 fine. And if you do it again, you are arrested. Do the telescope get disturbed by satellites? So no, not really satellites. The only disturbance we get from satellites are from, for example, the Starlink satellites. So this telescope at Green Bank is a radio telescope. So everywhere in Green Bank, there is this sign. So RFI reminders to guests. So at Green Bank, it is, if you visit Green Bank, your phone has to be off. You have basically no cell phone signal, no Wi-Fi, no television, no radio. So everything at Green Bank and these observatories, if you need communication, it happens through optical cables. So you will have an optical cable and then you will plug that into your computer and you'll still have internet and you can do it. So I took this picture on maintenance day. So for the Green Bank Astronomy Observatory, this is a hard drive cluster and the spectrometer. So the image on the left is 680 terabytes worth of storage. So how fast do you think that gets full? So that's 680 terabytes of storage. The Green Bank telescope does about 12 terabytes in 6 hours. So you can only imagine the data problem, and that is where we're also going to discuss this in one of our lectures. The big data problem is coming in. So the image on the right, I know this looks like a bit of chaos, but this is called a spectrometer. And it uses the information coming from a telescope to create a spectrum of the object being observed. And I will discuss a spectrum momentarily as well. So no, it doesn't take ages to read and write to those drives. So usually the drives that we use is 18 terabyte Western Digital helium drives. So another place I've also spent some time was at the University of California, Berkeley, where I was working with the CASPER group, so the Collaboration for Astronomy Signal Processing and Electronics Research. So if you ever have a bit of free time on your hands, Google Casper. They have some really cool projects and some really cool science that they are doing. And they are all operating from the University of California, Berkeley. So what do I do for my research? What is my interests in astronomy? So my interest in astronomy is astronomy signal processing. So if you look at an object in space and that data is coming through the telescope, number one, how do you interpret that data? And that is my field of research. How do you interpret the data and how do you get better devices, sensors on your telescopes to collect better data and to collect more sensitive data? So for my research, some of the devices I'm using this image is called a Roach2. It stands for Reconfigurable Open Source Architecture Computing Hardware. It is a FPGA, that's a field programmable gate array. So you get your normal CPUs and GPUs in a computer, but the CPU and a GPU is already specialized to do a specific task. So it takes a bit of a workaround To get a CPU and GPU to do something else, we get an FPGA, a field programmable gate array. That's a third type of processor. It's not specialized, it's completely open source, and you can use it for whatever you want. So I use FPGAs to create spectra of objects in space. So this right here is a spectrum of a methanol maser. So a maser is exactly the same thing as a laser. So laser stands for light amplification by stimulation of emitted radiation. Maser stands for microwave amplification by stimulation of emitted radiation. So instead of a beam of light hitting you, you have a beam of radio waves hitting you. And this maser is a molecular cloud that's usually in the star forming region. And if something in that star forming region happens and you have more electrons or energy moving through the molecular cloud, then the electrons jump to high valence orbit and radiates microwaves. So this is a 1024 channel spectrometer. And right here in the middle, we can see the response of a 4 megahertz filter, but not really on it. So if we create that's one, 4096 channels spectrum on that 4 megahertz filter, we can see this nice peak. And this nice peak is the chemical signature of methanol. And that is one of the objects we are observing. So now we can start putting definitions to everything. So astronomy is the study of the universe, the celestial objects that make up the universe, and the processes that govern the life cycle of those objects. So here we can see the South African Large Telescope, or SALT, and this is the largest optical telescope in the Southern Hemisphere. So when you guys ever have a chance to visit Sutherland and SALT, please do it. It is one of the greatest experiences you will ever have. But then we get radio astronomy. So radio astronomy is a subfield of the field of astronomy that is based to find methods and techniques to measure, capture, and analyze radio frequency electromagnetic radiation with the means of radio telescopes. So this image you're probably all familiar with is the Very Large Array, or short of VLA, in telescope in the USA. So if you are, let me ask, are you guys sci-fi fans? Then you guys all probably all seen the movie Deep Impact. It's a sci-fi movie from the 80s with Bruce Willis. And you've probably seen the first Independence Day. So this telescope features in both of those movies. So now we can get to what is the difference between a radio telescope and a optical telescope. So from your high school physics, you guys are all familiar with the electromagnetic spectrum. Okay, cool. So from the electromagnetic spectrum, we can see here gamma rays is on the left, long radio waves is on the right. On the top axis, we have our frequency, and the bottom axis, we have our wavelengths in meters. So the higher the frequency, the smaller the wavelength. So right here in the electromagnetic spectrum, we can see visible light. So visible light is part of the electromagnetic spectrum. So most optical telescopes is designed to look at only visible light, and some of them into the near infrared. So, such as the James Webb Telescope that's been launched can look at visible light and look at infrared. But the rest of the electromagnetic spectrum is not observed at all. And that is where radio telescopes comes in. So where a optical telescope looks at visible light and infrared, a radio telescope looks at the rest. So it looks at longer radio waves, AM, FM, microwaves, UV, X-rays, and gamma rays. So I will create the WhatsApp group in the next day or two. So yes, we will be discussing the James Webb Telescope as well. So you guys still following me with my explanation of the electromagnetic spectrum? And you guys understand the difference between an optical telescope and a radio telescope? Awesome. So if you guys have any question, please stop me. If you want me to re-explain something, I will. If you want to discuss something, just stop the class. You can type in the chat or you can unmute your mic and you can talk that way as well. So why are some stars not visible to us like gamma rays? So stars are visible to us in gamma rays. It all depends on the instrumentation we are using to observe that star. So if we want to observe gamma rays, we need a radio telescope that has a surface that will detect these large, small wavelengths. And secondly, the atmosphere disperses gamma rays. So therefore, we need these gamma ray telescopes at places that is extremely dry because the dispersion in the atmosphere happens due to water vapor. So these gamma ray telescopes needs to be at places that is extremely dry and extremely high so you can get away from water vapor in the atmosphere. So, you guys know about the CAT-7 telescope? So, in the early 2000s, when the Hartebeesthoek telescope was the only radio telescope in the country, the international community was starting to look at different ways to do radio astronomy. So, the two principles we have is we can either build one big giant telescope or we can build smaller telescope and in smaller telescopes and interleave them together, and the smaller telescopes will create one big giant telescope called an array. So there was the idea to build the SKA, the Square Kilometer Array. That will be the world's largest telescope because it will have a collecting area effectively of 1 square kilometer. So to participate in the bid for the telescope, South Africa needed to demonstrate that we have the know-how and resources to operate, design, and build radio telescopes. So the first prototype was built at Hartebeesthoek that we are still using today. It's a 15-meter telescope. And then 7 more of those were built in the Karoo, and it stands for CAT, so the Karoo Array Telescope. And there were 7 of them built that's still being used today in the Karoo. So this is near Carnarvon. From these 7 telescopes, the design changed a little bit. So if we go back to this design, we can see we have the struts and our receivers and detectors in the front. So the incoming electromagnetic waves will, let me get my pointer. Can you all see the pointer? Okay, so electromagnetic waves will come in, hit the surface, and that will be reflected to our detectors, and then we'll be able to analyze the data. But one thing of this design is these struts block a little bit of the surface area of the telescope. So this has been redesigned as an offset Gregorian. So we will have our main reflector here. This right here is called a sub-reflector, and the receivers and sensors are down here. So the radio waves will come in, bounce on the service to the sub-reflector, from the sub-reflector down to the receivers. And then 64 of these were built in die Karoo, so meerkat, so meer Afrikaans vir nog, so more of the CAT telescope. So due to the CAT telescope success, we got the bid to create and host the SKA telescope. So the meerkat telescope became 64 of these dishes. And for the SKA, this 64 dishes will become 4,500 dishes. So this is currently a part of a section of the Meerkat telescope. And you've probably all seen the great images from the Meerkat telescope that's been released recently. So yes, there is certain distances between each one. So we need the effective area covered. So if you add all the surface areas of all these telescopes, eventually it needs to be 1 square kilometer. But the distances of these dishes are a certain distance apart. So the few part in the center is only a couple of 100 meters apart, only a couple of meters, so between 10 and 20 meters. Then you get to the next outer ring, that's a couple of 100 meters away. And then the next ring will be another couple of 100 meters away until you eventually reach the 1 square kilometer. So how much does these cost to build? So this is a lot of money to build these telescopes. I'm not sure where the cost estimate are for the total SKA, but I know for Meerkat there has now been approximately 600 million euros being spent to build the Meerkat telescope. So yes, we are going to learn in detail about some of these telescopes and objects that they are observing. And where does the funding come from for these telescopes? So the funding comes from government and also from collaboration with other countries. So, for example, the Meerkat telescope, South Africa will give the majority of the funding. That means when a telescope is in operation, South Africa will have most viewing time on the telescope, but other countries that contributed will also get viewing time on these telescopes, depending on how much their contribution was. And then to use these telescopes, such as, for example, SALT, the Hartebees Hoek telescope, we have a research committee sitting at the NRF, so the National Research Foundation, and you submit a research proposal on why you want to use a telescope and what you want to observe. So if it's something worthwhile, you get allocated a time slot on the telescope, so you can be at the observatory itself when the observation happens, or the observatory just does the observation for you and just sends you the data collected from the telescope. So currently at Hartebees Hoek, our telescope is currently now scheduled 18 months in advance. So can telescopes make a profit? So to make a profit, we don't really think about economics on it. So we do astronomy to do research. So to find out what's out there, how does the universe work? So it's not for any financial gain. But usually the technology being developed on these telescopes get patented and you can make some money off that. But the main cause is not to make money off these telescopes, but to do research with these telescopes. So unfortunately not. So we will not be learning about plants in this module, but rather what is in space. So this image is a few images of the CAT telescope. So we can use this telescope to identify UFOs. Yes, in theory, we can use this telescope or these telescopes to identify UFOs. So in this image, each red speckle you see is a distant galaxy. So right here in the top left corner is CAT 7 in 2012. So this big image here in the front is at the center of our Milky Way galaxy. The image to the right of it is Meerkat, 4 of the 7 editions in 2016. And here we can see the central bulge of our galaxy. And all these other dots are other galaxies in the background. So if we use the 16 of the 64 dishes of Meerkat in 2016, here we can see the supermassive black hole in the center of our own galaxy, the radio jets that's being expelled by the center of a galaxy and a supermassive black hole. And all these red other dots are all other galaxies in the background. And then if we use the 16 of the 64 dishes of Meerkat in 2017, here we can see the center of our galaxy in a lot more detail. And here we can see other galaxies still in the background. Is everyone still following? Awesome. And this image was in 2018. So this is the full 64 dishes of Meerkat. So here we can see this in the middle of our galaxy, our supermassive black hole, the radio jets being emitted around this black hole, and a lot of different galaxies in the background. Do you all recognize this symbol? So are you all familiar with the Event Horizon Telescope? So this is the logo of the Event Horizon Telescope. So the Event Horizon Telescope is an array of telescopes. We call such an array a VLBI array. So VLBI stands for Very Long Base Interferometry. So there you have a lot of telescopes around the world, and these lines form basebands between these telescopes. So these telescopes look at the same object at the exact same time. Each telescope has a little bit of different resolution and a bit of different design. So each telescope will create a unique image of the object being observed. And then by using these basebands, we can create a virtual telescope that is as big as these basebands, and that is called VLBI. So is there a way to adjust the focus on these telescopes to make? Yes, there is. So everything is done in processing of the data. So if you go back in these two, so this looks fuzzy because this is just raw data that hasn't been enhanced, but you can get much better images of it. So coming back to this image, so you all have more or less idea of what VLBI is. Okay, so let me try and explain this again. So VLBI stands for Very Long Base Interferometry. So you have telescopes around the world looking at the same object at the exact same time. So each telescope is unique in its own way. So it's same as us humans. So none of our eyes are the same. So if we are looking at something, Depending on your eyesight, you will interpret the image differently. So when we get the data from all these telescopes, for example, those people who's in photography, we layer all the images and we get a nice 3D model of the object being observed. And that is the essence of VLBI. But what is cool about VLBI is you see all these lines connecting all these telescopes together. Is called basebands. So you see this forms short of a triangular sphere. So we can create a virtual telescope with a mirror the size of these basebands or these lines. So then you create a virtual telescope that is basically the size of Earth. So why is there yellow and blue? So it all depends on which network of telescopes is being used. So we have the VLA, that is basically the American VLBI. We have the VLE, that is the European VLBI network. We have the African VLBI network called the AVN. So this is just the naming conventions. So what are the limitations in terms of image quality? Do we need more computing power or better engineered dish telescope? It's a combination of everything. So we need more computing power, we need better engineered telescopes, we need better instrumentation. So everything comes together in the quality of image we get. So this combination of telescope, this is about 8 telescopes. But do you know why these telescopes were chosen for the Event Horizon Telescope? So these telescopes were selected because they are the only telescopes on Earth that can detect X-rays. And we need X-rays to detect a black hole. I will come to that in a moment. And all these telescopes can detect X-rays, which means their optics or the surface area is smooth enough and doesn't have imperfections so you can detect X-rays. And these telescopes to be able to detect X-rays are on extremely dry places or extremely high places. So that's why they were used. So question, what is the theoretically furthest we can see or the furthest back in time we can see? Is James Webb the limit since it looks for redshift objects? So the furthest back we can actually see is the Big Bang. So that is something we will discuss in one of our lectures, but the look back time on the Big Bang is roughly 13.8 billion years, and that's how far we can look back. So in each telescope monitored by the country is it in, or does one country place them in multiple countries and monitor them? So the country where it's placed is monitoring it. So for example, at Hartebeespoort, where I am about half a week, we have observatory staff at the observatory that runs the observatory. So example, the Green Bank Observatory, the observatory there has staff monitoring that observatory, and that is controlled by that country. But for example, the telescope we have in Antarctica, we can see here, is a collaboration between different countries. So there is a staff of people manning that telescope as well. Yes, stars are visible in the X-ray part of the spectrum as well, but I will come to a moment why we need X-rays to detect black holes. So so now question, where do black holes lead to? We have no idea where black holes lead to. So currently all the physics we understand comes to where a black hole is. But inside a black hole, we have no understanding of our physics, and our physics starts to break down. So that is one of the fields of physics that still needs a lot of work. So for example, in developing algorithms for these telescopes and for the Event Horizon Telescope. So this is I got from the director of the Event Horizon Telescope that visited Akweshoek back in 2017. So one of the algorithms to test and to filter through the data automatically is they decided to give it a lot of pictures of jam jars, and this is what the algorithm came up with. Then the image on the right, they asked for chocolate chip cookies, and this is what the algorithm spit out. So since then, the algorithm has been fixed and is working properly. So is a wormhole and a black hole the same thing? No, they are not the same thing. So we will delve slightly information paradox and such things. Yes, we will touch a little bit on it. So in the 1970s, this is what we imagined a black hole would look like. So no one is able to see a black hole because light cannot escape a black hole. So how do you actually take an image of something we cannot physically see? So question, would space weather forecasters be employed by space agencies or observatories? Yes. For example, the South African National Space Agency use meteorologists. And would space weather forecasters be employed by space agencies or observatories? Same question. So yes, they will be used by space agencies because you need to know, for example, when is the great opportunity to launch something into space. You need to, optical telescopes can't see through clouds, so you need to monitor that as well. And at these observatories, we do research on weather as well. So this is where I ask for X-rays. So how do you guys think we take an image of a black hole if not even light can escape a black hole? So how can we take a picture of something that sucks in light? Yes, Mr. Van Sale, that is correct, and the other guys as well. We look at what is around a black hole. So the easiest thing we can see what's around a black hole is X-rays. So the black hole, we will learn a lot about this later in this module, but a black hole has a point around it, or you can call it a fence or perimeter called the event horizon. So everything in front of the event horizon can escape the gravitational pull of a black hole, but everything beyond the event horizon gets pulled into the black hole. So when we have matter being pulled into a black hole and it starts orbiting the event horizon, it starts moving faster and faster and faster the closer it gets to the event horizon. And this particles now moving faster, faster, and faster gets bumped into one another, and they will start sharing and losing electrons. And eventually, due to this increase of speed, increased temperature, increased pressure, it will start emitting X-rays. And these X-rays we can see around the event horizon. So the image of a black hole that we have is X-rays being emanated around the black hole. So the Event Horizon Telescope program has done a lot of computer simulations of how a black hole would look like if we would image it through the radio telescopes and the radio telescope network called the Event Horizon Telescope. And this is the best simulation of the image. So you all remember about 2 years ago when the first image of a black hole was released, that was in 2020. This is actually how it looked like. So right here, this is the black hole where everything gets pulled in. This right here is the X-rays moving around the telescope. This side is brighter because it's moving in our direction. So this is a bit of a Doppler effect, red shifted, blue shifted. So this is moving towards us. And the other side are a bit more hazy, and that is because we see it moving away from us. So yes, we will learn a little bit about relativity as well. So why does it look 2D? Why is there no orange in front of it? So this is, if I remember correctly, M86 or M84. So this black hole is positioned at the center of the galaxy, is looking directly towards us. So if you have a plate and you pick a plate up off a table and hold it directly to your face, you will see the plate head on, not from the side. And that is exactly what we wanted for the Event Horizon Telescope, so we can see it from head on and not from the side as a disk. So yes, it doesn't surround it. So this is spinning around the black hole. So is this process the same of increasing of heat and pressure results in stars producing X-rays? Yes, that is the same idea, but we will discuss that as well in depth in this module. So some of the interesting objects we will be learning about in this module. One is pulsars. So when a star reaches the end of its life cycle, depending on the size and the mass of the star, a few things can happen. If it's above a certain size, the star will go supernova, meaning it will blow itself in bits, and the core will implode on itself and become a black hole or a neutron star, depending on, again, the size of the star. Or if it's a smaller star like our own sun, then the sun will basically just die out and become a red dwarf, then a brown dwarf, and then just a rock floating in space. But a pulsar is a star that went supernova and the core imploded on itself to become a neutron star. And certain parts of its surface is still radiating energy, but due to the fact that the star imploded on itself, it got squished into a tiny ball. And with this implosion, the density became extremely high, and due to the density becoming extremely high and the radius becoming smaller, you still need to conserve angular momentum. So this neutron star usually spins around in a couple of nanoseconds. And if it's radiating still energy in a part of its surface, this spinning neutron star flashes a beam of energy towards Earth. So you can basically think of it as a lighthouse spinning around, and every couple of seconds or every couple of nanoseconds in a neutron star, we will see these flashes, and that is called a pulsar. But we will discuss that in this module in depth. Then we will also look at quasars. Quasars are very luminous and very energetic objects that are in the center of galaxies. We will also look at masers, so microwave by stimulated emission of radiation. So a laser is just light wave by stimulated emission of radiation, so maser just microwaves. So these masers are molecular clouds in space. They usually are in star-forming regions. And masers are good indications of what is happening in star-forming regions. Like I said previously at the beginning of this lecture, in a star-forming region, if energy moves through one of these molecular maser clouds, the electron jumps to high valence orbit, irradiates microwaves, and then we can see it, and then we can point our telescopes to that area and see what is going on. So question, are supernovas the largest explosion in the universe? Yes, so supernovas is the largest explosion in the universe. So something interesting for you guys to think about supernovas. Do you guys know all the heavy metals on Earth, such as gold, silver, platinum, uranium, isn't naturally occurring on Earth? So where do you guys think these elements come from? Yes, they come from stars. So these elements come from, more precisely, supernova explosions. So these supernova explosions creates these elements, and then when planets form around stars, they basically steal the degradation of all these objects, and that is where the composition comes from of gold, silver, platinum, uranium, and other elements. So that is another thing we are going to discuss in this lecture. So this right here is an image of a solar eclipse captured by the Green Bank Observatory. So the Green Bank Observatory has 19 telescopes. So the biggest one is we call it the GBT, the Green Bank Telescope, the 110 meter diameter one. But this is captured by the Green Bank 20 meter telescope at 9 gigahertz. So here we can see the moon moving in front of the sun and blocking out a part of the electromagnetic spectrum. So another comment, and we are atomically connected to all atoms in the universe. We are not figuratively, but literally stardust. Yes, that is correct. So I assume you are a fan of Neil deGrasse Tyson as well. So let me ask you a few questions, or just have a bit of a discussion. So you all said, so majority of you, I assume, are sci-fi fans? That's great. So what sci-fi are you interested most in? Interstellar is a great movie. The Martian is also a great movie. And some of the two great sci-fi franchises is probably Star Wars and Star Trek. So that is all great. So I like it that you guys are sci-fi fans. Oh, Hitchhiker's Guide, another cool one. So, who of you guys have an interest in astronomy and astrophysics? Awesome. Then you will love this module and what we are going to do. So hopefully this module will prickle your interest in astronomy, and perhaps it will change your mind to pursue a career in astronomy. So just to get a feel of the class, I see majority of you are computer science students. Awesome. And then there are obviously as physics students. Yeah, I see you commenting right now. What other fields or what other majors are in this class as well? Geography. What other majors is here as well? So the latest class list chemistry. So the latest class list I look at is we are about 136 students registered this module. This can change the next few weeks, next 2 weeks, more student registers or few deregisters, but I expect the class numbers to remain more or less the same. So I'm doing physics with a second major meteorology. That is very cool. So in the next few days, latest tomorrow, I will send out a link to a Google Sheet that you need to fill in. In a Google Sheet, I need you to fill in just your name, student number, number I can use for WhatsApp, and if you have connection issues for online classes, for example, not stable, even a connection, something like that, just for statistics for me to use. And I will also give you a link for a Discord channel. So one thing with the WhatsApp group, I will kind of please ask you guys is there's going to be a few rules. The first one is please keep the time of day in mind. So I know previous years you get some unholy messages at 1 o'clock, 2 o'clock in the morning where a student will ask you for help with something. Please, if that is within reasonable hours. Secondly, don't spam the groups with advertisements and uh, other nonsense. So we keep it strict to the module and to astronomy. So, come on, sir, this lecture has me feeling I have lived under a rock. So this is exactly the idea for this module, is to give you an introduction of what's happening in the world of astronomy. So after this module, if you want to pursue astronomy, then you can pursue astronomy. If you don't want to pursue astronomy, then you can do that as well. But this is to give you an overview of what is going on. So in second year, there's a module that's going to cover the same topics as what we do in this lecture, but then you're going to do in-depth physics behind everything. So this is just to give you an overview and a bit of physics, but in second year, you're going to do this in much more detail of the physics around it. And then if you choose the astronomy major course, then you can have some astronomy modules in your third year and then an honors as well. So ladies and gentlemen, this was the introduction lecture. You guys are more than welcome to log off, and I will see you all tomorrow night where we will start with our first proper lecture. I will be active for another minute or two if you have more questions, but otherwise have a wonderful evening. So I see you have your hand raised, Mr. Sanelli. You have a question that's off topic. You can type it in the chat or you can unmute your mic and ask the question. Yes, so those of you who do not know much about astronomy, you'll be 100% fine. So the idea with this course is that you don't need any science background at all to follow what's going on. For some details, so just hang on. I will, in the next day on Blackboard Collaborate email, send you guys a link for a Google Sheet. So have I watched Attack on Titan? No, I haven't watched Attack on Titan yet. So by when should we purchase the textbook? So ideally as soon as possible, but I know sometimes finance is a bit of a problem. So if you know where to look online, you can get a PDF version and I don't mind. So what's the name of textbook? I will give that in the study guide. So that is the Horizons textbook. So let me quickly go to the slide of the Horizons textbook. Where is that? So here is the prescribed textbook. So if you want details on it, it's Horizons Exploring the Universe, the 14th edition. Of course, if you need a class rep, I am more than happy to help. So we just need to figure out, because COVID has stopped a little bit of class rep. So if I need a class rep, I will give you a shout. Thank you for volunteering. So on ClickUp, the module is still locked for me. It shouldn't be locked. It was unlocked today. So just make sure if you refresh the page, if it's not unlocked, if it's still not unlocked by tomorrow, just send me an email and I'll see what I can do. So the open source textbook, the link is also in the slides and there will also be in a study guide. You can just download it. So you don't need to go over specific work for tomorrow. So tomorrow's lecture, we will go through what units of measurements we use in astronomy. So we will start looking at stuff like the parsec and light year and just the scale of where we are operating. No, I haven't read the end of everything. Is the good book? Yes, I will upload the slides on ClickUp in the next hour. It's a pleasure. So what is the difference between astrophysics and astronomy? So in astronomy, there's a few different aspects of astronomy. So you can say astrophysics is a subfield of astronomy. So astronomy is focused with everything out in space. So in astronomy, you can do research and work on instrumentation, how to build better telescopes, how to build better instrumentation. You can do in astronomy, you can be on the data processing side, find better ways to store data. But astrophysics specifically look at the physics behind these phenomena and objects in space. So when will the study guide be released? I will try to release it tomorrow, the latest at the end of the week. Oh, cool. I will definitely get a copy of that book. When you say basic mathematics will be needed for this module, what is the definition of basic math? So it's basically just going to be multiplication, subtraction, plus minus. So basic algebra. It's a pleasure. So states will have 4 lectures per week, but only Monday and Tuesday times are provided. There's roughly 2 hours each. So yes, so if you look at the time schedule, we are 4 lectures per week. So that means 4 periods per week. So on a Monday evening, we have a double period. On a Tuesday evening, we have another double period. So that is our 4 lectures. So basically, we will only have Monday and Tuesdays. So if I don't want to branch into astronomy, what will this module help in terms of a career? So this will just give you a broad knowledge of what there is in science and what is out there. It's a pleasure. I'm glad you guys enjoyed the lecture. So if there is no more questions, then I'm also going to log off. So all of you have a great evening. Good luck with the classes tomorrow, and I will see you all in tomorrow's class.